Okay, so this is my second video on node voltage analysis, and what we'll be doing today is node voltage analysis using or with a circuit with a current dependent current source. So as you can see here, 3ix over here is a current dependent current source, and it depends upon the current ix going from node 1 to node 2 through the 8 ohm resistor. So what we can do is, as I taught you in my first video, we're basically looking at the currents that are going in and out of the node. So real quick, if we look at node 1, we got three currents, one coming in from the left, one going down through the 24 ohms resistor, and one going to the right, which is just ix. And what we can do is, using the KCL, 0 equals minus 3ix since it is going in. So as I told you earlier, whenever a current is going in, we take it as minus. So 0 equals minus 3ix plus v1 by 24, assuming it's going down. And the third current is just v1 minus v2 by 8 ohms, which is just ix. So since this is our ix, v1 minus v2 by 8. Now ix equals v1 minus v2 by 8. Now if we just substitute that into our equation for 3ix, right here I've substituted for 3ix, and we can just go ahead and solve the algebra. So what we get is, this is our final equation for the circuit at node 1, which is minus 5v1 by 24 plus 6v2 by 24 equals 0. So now what we're going to do is go ahead and do the same thing on node 2, and we'll get our second equations. And two equations with two unknowns, v1 and v2, we can easily figure out what the voltages are. Okay, so I just want to make a small correction to the circuit. So the circuit is connected to ground through the bottom nodes right here. So when I'm talking about the current going down from node 1, it just means that it's going from node 1 to ground. So I hadn't drawn the ground on the circuit that I showed earlier, and even for the next part, when I'm going to do the node voltage analysis from node 2, I don't have the ground written there, so I want you to assume that there's a ground over here. Okay, now for the node voltage analysis at node 2, we have three currents, one from the left, one going to the bottom, and one from the right. So it might seem a little confusing because we have ix going in, and you might be confused about what do we put as the sign for it. As I've told you earlier, whenever current is going inside a node, it's going to be minus, and whenever it's coming outside and going out of the node, it's going to be plus. Okay, just take a look at the first one from the left. What we do is ignore the ix over here and just see at the nodes. So it's going to be v2 minus v1 divided by 8 ohms. So there's the first current here. The second current going to the ground, it's v2 minus ground divided by 16 ohms. And here we're given 6 amps going in, so that's just minus 6 amps going in. So using Kirchhoff's current law, we have 0 equals v2 minus v1 by 8, which is the current from this, v2 minus v1 by 8, which is actually just minus ix. And we have v2 divided by 16, v2 divided by 16, which that's because v2 minus 0 ground divided by 16. Then we have minus 6 amps coming in. So if we write down the equation, 0 equals the current from the left hand, the current going to the ground, and current coming in from the right. So we go ahead and solve the algebra, and here we have our second equation. 6 equals v1 by 8 plus 3v2 by 16. Okay, for the final part, we're going to find the values of v1 and v2, and I'm going to use Wolfram alpha to do that. So what I've done is for V1 I've put in X, as you can see right here. There's X, and for V2 I've put Y. So V1 is X and V2 is Y. So I put two equations, 0 equals minus 5V1 divided by 24 plus 6V2 divided by 24. So, and the second one, 6 equals minus V1 divided by 8 plus 3V2 divided by 16. And as I told you earlier, V1 is X and V2 is Y. So the Wolfram Alpha goes ahead and solves it and gives me the solution as X equals 192 and Y equals 160, which just means for that our purpose V1 equals 192 and V2 equals 160.